I want to do a few videos about irrational roots. Our main concern with number theory, at least at this level, is not with irrational numbers, but it's good to um, to get some exposure to some of the things we could prove about rational or irrational numbers. And I want to start with the claim that root 5 is irrational. It's very like the claim that root 2 is irrational. I'm going to show you a proof, but I don't really want to call it a proof exactly. It's more of a sketch of a proof or a plausibility argument because there's going to be some gaps in it. And those, I don't think any of those gaps are going to be um, unconvincing. I think the proof is going to be convincing. But I want to point out that some of the holes in it that we're going to fill progressively in the first couple of chapters of the book when we really think very carefully about the ideas of number theory. Um, One of the themes of this course is why do you prove things carefully? And so I'd like to think about it's a little bit of a far-fetched idea, but this is what comes to mind. Suppose that you are inventing a secret code based on the decimal digits of square root of 5. And one of the things that's really bad, you need various things to make a really good modern code, but one of the things that's terrible is repetition. And so if you're using the digits of square root of 5 and they repeat, maybe after a billion digits, it could still be horrible. You could be encrypting some like multi-gigabyte file with very sensitive information. And if this is secretly rational and you didn't know, then you could have a somebody could break your code. Okay, so fairly implausible because it's a 2,000-year-old result. But that's the kind of level of care we want. You want to imagine that there might be some tiny, tiny little chance that you missed something, but if you miss something, people die. So let's think about that. Think about it in that way. Okay. So we'd like to prove that root 5 is irrational. Okay. We're going to prove it by contradiction. So I could have called this part 9 of proof by contradiction, I guess. Assume that it is rational. So here's the proof. Assume root 5. Okay. So I'll just say that in symbols. It's equal to p over q, where p and q are integers. Okay. And in fact, let's say positive integers. If they were both negative, we could just negate them. And P and Q share no common factor. In other words, that fraction is in lowest terms. And we're going to take that assumption and try to drive towards a contradiction. So a couple of comments about that, about the logic here. Are we absolutely 100% sure, as in like lives are at stake, that we can do that? That we can write a fraction in lowest terms. Have we ever proved that? No, we haven't, because we're at the very start of a number theory class. Okay, so that's something we want to be really, really careful about. That makes sense, that you can write a fraction in lowest terms. It won't be hard, but we haven't actually proved it. Okay, and again, I think proof by contradiction really highlights the necessity of being really, really careful. We're making this assumption, and we want to drive towards an absolute certain contradiction. And we want to show that just this assumption and nothing else led to an impossibility, and therefore this must be impossible as well. But what if somewhere along the way we introduced something else that was kind of dubious? Then we wouldn't necessarily be able to conclude that this was the only problem. Okay, so that's going to be, I'll put a little star by, that's one of the things that we're going to need to actually be careful about. And this is again just a sketch of a proof, really. Okay, so now I'm going to square both sides. Okay, now that, I think we're going to assume that we really know how to just do basic arithmetic with integers and rational numbers and things like that. And by definition, squaring the root 5 gives 5. Okay, so I'm not going to star that as a worrisome thing. Well, let's clear the fraction because that's much easier to deal with things that aren't fractions. So 5q squared is equal to p squared. Okay, so in other words, 5, we've written p squared as something times 5, an integer times 5. So 5 divides p squared. Remember the notation for that is 5 vertical bar p squared. Okay. All right, what can we say about that? Well, we'd like to say something about p, not just p squared, because that's sort of what started this argument, talking about p and q. Okay, let me erase up here. And I claim that means that 5 divides p as well. Okay. Now that's definitely deserves a star. Okay. You should think about that. I think it's pretty plausible. But there's something special about the number 5 that we're using here. If I had 4 dividing p squared, there's no way I could say that 4 divides p. Okay, because p could be 2, for example. Okay, so there's something very special about 5, namely that it's prime, or at least that it's not a square, really, not a perfect square, that says that, in fact, the only way that 5 would divide p squared is that 5 divides p. So we could do that as a little proof by contradiction. We could try to set it up as a little proof by contradiction within the proof by contradiction. If 5 does not divide p, then it seems like, how on earth would p squared suddenly get a factor of 5? Because when 5 is not the square of anything. Okay, but we really haven't quite gotten to the stage where we can be super confident about that either. We haven't talked a lot about the specifics of divisibility. Okay, but so that's one of the claims we'd like to have to keep the proof going. Okay, now here's the cool thing. If 5 divides p, okay, then 5 squared actually divides p squared. So this is a kind of an interesting argument that we knew that 5 divides p squared. Then we're saying that p itself must have a factor of 5. But you know what? P squared was that squared, and so it's going to have a factor of 5 squared. So more than you would expected. Because it's a square, it can't have just one factor of 5. Eventually, in chapter 6, we're going to get to the fundamental theorem of algebra, which tells us that every integer has a unique prime factorization, and these statements will be very, very obvious if we believe that. But we really have to prove things that are much more basic about divisibility to even get to the fundamental theorem of algebra. Okay, so 5 squared divides p squared, but wait a minute, that was equal to 5q squared. Okay, so let's be really careful about that. Don't want to make this too long. It says that 5q squared is 5 squared times something, like k. Ooh, cancel one of the 5's. Q squared is 5 times k. Hey, so now q squared, 5, divides into q squared. Same argument, if we believe that, tells us, so that's that same star, that same idea, 5 divides q. Okay, wait a minute. 5 divides p and 5 divides q. That's suspicious. Okay. But I asserted that I already picked p and q to have no common factor. Have no common factor. And there's our contradiction. Okay. So if you look at the structure of the proof, it's really about this idea between when you have squared integers, what can they be divisible by or not? And it really turns on the fact that they can't be divisible by just one copy of a prime. If they're divisible by anything, they have to be divisible by 2. And then that gives you unexpected amounts of divisibility by 5 here between p and q. So that's how the proof works, but there are some real holes to be patched about divisibility and about this idea of, can you always put a fraction in lowest terms so that they have the numerator and denominator have no common factor. Okay, so that's a classic kind of proof of to really be pretty sure that a certain number is really irrational.